if Andrew can. Okay, perfect. Okay, so over to you, Pablo.
Thank you. So first of all, thank you so much for inviting me here today. So I would like to tell you about a recent work we have done together with Julius Lemon, Tibor Rakowski, and my supervisor, Frank Pullman. So in this work, we kind of continue studying what is the role of symmetries and their associated conserved quantities and the dynamics of many-body systems. So we are familiar with conserved quantities like these U1 charges, which I will denote in the following U1 charges, like particle number, which is just a sum of some local densities, uniform sum of local densities along space, or say total magnetization, which is the conservation of the spin components along certain direction, as well as other discrete symmetries, like, for example, fermion parity or the Ising symmetry. So the invariance, for example, of the whole Hamiltonian, Ising Hamiltonian, and they're flipping the sigma z operators. However, quite recently, people became really interested in other family of less conventional symmetries. And the reason I call them less conventional is because you don't really expect to find them in nature in daily life basis. And the first family of these conserved quantities are dipole and higher moments. So these you can think is the center of mass or the first moment of these U1 charges. And conservation of this quantity imposes really strong constraints on the dynamics of kind of fundamental charges. So for example, this single charge cannot freely move if the total dipole is conserved, but instead has to emit a dipole in the opposite direction. And this applies to some higher moments where in general you have some finite order polynomial of the coordinates multiplied by this local density. And another family of these unconventional symmetries are so-called subsystem symmetries. So here, for example, in this first kind of family, you find that not only the total charge is conserved in the whole system, but also along every column and every row of the lattice, and also kind of discrete examples of this, where you might have a symmetry transformation which only acts non-trivially on certain fractal structure of the lattice. And the reason people became interested in this kind of unconventional symmetries is because they appear to lead to rather novel and interesting phenomena. So although I will mostly focus on the out of equilibrium, well, on the dynamics of this system, it's worthy to notice, like at equilibrium, this can give rise to so-called fracton phases, which you can think of as some generalized notion of topological order. The presence of these U1 subsystem symmetries also led to the generalization of the so-called symmetry protected topological phases. And finally, there was the suggestion that in the presence of such C2 or fractal symmetries, you would have some fractal spin liquids, or even people investigated fractal quantum criticality. So there's continuous symmetry breaking of such symmetries. However, in the kind of this talk, as I said, it's mostly focused on the dynamics or out of equilibrium. And in this regard, for example, it has been shown that the presence of dipole and higher moment conservation, together with finite range interactions, would give rise to some so-called heat fragmentation, also known as reducibility in the StatMech community, which basically means that if you fix your global conserved quantities, in this case, charge and dipole, still your Hilbert space would split up in exponentially many sectors, which cannot be simply labeled by some global and local conserved quantity, but rather some additional kind of non-local degrees of freedom in this case. The presence of dipole has been also in higher moments, has also been shown to lead to sub-diffusive transport of the charge or the spin-spin correlators. And this has been nicely first found in this experimental work by the Princeton group. And later on, there were a set of different theoretical generalization or extensions of this behavior. And finally, although I said these are rather unconventional symmetries that a priori you don't expect to find them in nature, they actually appear as some effective description of many body systems, interacting many body systems in the presence of a strong tilt. So a tilt you can imagine as some uniform electric field or some strong gravity field, which in this strong limit would basically give rise to processes where, say, one particle goes up the tilt, the other one goes down the tilt, and which will give rise to the conservation of the dipole moment. And in fact, this is related with the so-called Stark many-body localization, which is a proposal of disorder-free localization, which would have similar features as the usual MBL phase. So there has been a lot of interesting works, but perhaps I would like to highlight that not only dipole conservation, but other family of kinetically constrained models can emerge in this kind of really simple experimental setups when you start kind of playing with resonances between the interaction strength and the field. So if you step back and look at this family of unconventional symmetries from a more kind of general point of view, you would realize that their conserved quantities are always of the same kind, are especially modulated quantities. And by this, I mean that there is some local density, so it's a sum, some weighted sum of a local density with some function that depends on the spatial coordinates. So for example, in the case of dipole and higher moments, this modulation is given by some finite order polynomial of the coordinates of the space. Or for subsystem symmetries, you can think that this modulation is simply some indicator function which takes non-zero values along certain submanifold of the lattice. So this talk is about, we wanted to answer the question whether we can extend this family of modulated symmetries, whether there is something else, to understand whether we can provide microscopic models hosting these symmetries, and eventually, and inspired and motivated by these previous works, whether we can understand the effect on the dynamics that these symmetries have. So before starting into that kind of trip, let me briefly mention kind of the numerical tools we are going to use. So we are going to consider a stochastic block cellular automata evolution. So let me summarize it first. So you can simply think this is a Markov, local Markov evolution that will update string configurations to some other string configurations, okay? So you will pick up some random initial configuration of the spins, and this will be, say, a string of size L or L+1, where the local spin degrees of freedom just take half integer or integer values between -s and s, okay? So once we have our initial configuration, we will apply a subsequent application of layers formed by adjacent local gates, which in this particular case are going to act on 2 neighboring sites, but in principle, they will act on 3, 4, and some kind of local nearby region. And basically what we will study is the evolution of certain quantities along this time evolution. So if you wish, for those that perhaps are more kind of familiar with kind of quantum circuits or something like that, this is like a particular case where we are mapping the string states in the set basis, if you wish to states in the set basis, and we will just random average of a random initial kind of configurations. So what we need to then specify are the local gates, right? So the way we are going to specify the local gates for the study of these symmetries is going to be basically we are going to identify two integer numbers, or let me say a different way. We are going to have as many integer numbers specifying the gate as the range of, or as the size of the gate. So in this case, it's a gate of size 2. So we will have 2 integer numbers. And the way they are going to locally act is by updating the local spin degree of freedom by raising or lowering the spin by ni units. As long as the resulting state, okay, still lies within -s and s. So let me give you, let me give you an example. Say we fix the spin to be 1/2, and say we pick up the gate +1 -1, or as you see here, the inverse. So we will roll a dice, and if the result is 1, 2, or 3, we will apply the gate +1 to -1. Assume we have this spin configuration with up, down. Then if we try to raise the spin up by yet another unit, we will leave this subspace of the spin 1/2. So what we do instead is leaving the state invariant. If on the other hand, we got a 4, a 5, or a 6, we will apply the reverse gate, so -1 +1. And what this will lead is just some swap operation between the two spins. So if you wish, in this particular case, what we are formulating is an unbiased random walk. So the spin up is a field site, the spin down is an empty site. And for example, if you ask questions of how this spin at initial time relates to another spin at some later time, in the long time, you would find that this correlation is described by some diffusion equation. Okay. So what we will do once we have certain kind of run finished, we will average about different random initial states and circuit realizations, where we are applying the gates completely randomly, although here I put a particular kind of big wall structure, the structure will be completely random, and then we will average the results over that. Okay. So the goal, as I told you, is to understand whether we can extend the family of modulated symmetries. So the plan for the talk would be, we will first introduce a set of one-dimensional models, toy models, to characterize these symmetries and understand the role of the dynamics. And then we will generalize this to higher dimensions, where we will find that the same construction works and where all these symmetries will be combined. Okay. So let me introduce these models. So I'm going to consider range 3 gates, and I'm going to specify them then by 3 integers, which are going to act as like lowering the spin at the center by p units, okay, and raising the spin on the sides by q units. So if this picture is still really non-intuitive, that's really useful, let me give you the corresponding quantum Hamiltonian that would have some kind of similar structure, okay? So you can think the dynamics is governed by some raising and lowering operators, so some powers q and p, and it's acting on a local Hilbert space that is sufficiently large such that the dynamics are not trivial. So say if I'm considering q equals 2, I shouldn't use a spin 1/2, but some larger spin. And what we will find is that none of the results change if we take sufficiently large spins, okay? But everything I'm going to do is completely classical, and I won't discuss anything that has any relation to quantum, okay, in this talk. So we know how to answer this question. So we want to answer, I translated the question to something simpler. We want to answer the question, can we find such a continuous symmetry for any choice of q and p's? So we already know how to answer this question for the particular case of p equals to 2q. So in this case, say I choose q equals 1, what we have is some symmetric distribution of charges from the central side to the sides. And this will just lead to charge and dipole conservation. So we will recover the previous results. However, what is more interesting is what happened for any random choice of q and p. Is there such a conserved quantity? And what you find is that answering that question is exactly the same as being able to solve this linear recurrence equation for the weights that appear in this modulated symmetry. However, you notice that this is a linear recurrence equation, so we can always solve it by finding the roots of the associated characteristic equation that can be written as a function of p's and q's. And after we fix some initial conditions or some boundary conditions. So say I have open boundaries, okay, for the moment, and I fix the first 2 initial conditions, alpha naught, alpha 1, I can recursively solve this to the right. And what this means is that for any choice of q and p, I will be always able to find such a continuous symmetry, which at first I found quite funny because apparently there was no structure. So let me show you the possible scenarios we can find. So first of all, we know dipole conservation is one of the possibilities, and this happens for p equals to 2q. In this case, you find that the characteristic equation has a double degenerate root that is equals to 1, and you just recover that indeed charge and dipole is conserved. Okay. However, what is more interesting is that there are 2 additional answers to this question. The first one are the exponentially localized symmetries. So what you find here is there are 2 positive roots. The first one is greater than 1, and the second one is smaller than 1. So the reason why this happens, just as a small remark, is because this characteristic equation is, the polynomial is so-called self-reciprocal. So the factor in front of r squared is the same as in front of 1. So if R1 is a root, the inverse is also a root. Okay, so they come in pairs. They always come in pairs for these models. So this means that if you have a system with open boundary conditions, there will be exponentially localized conserved quantity to the left boundary and another one on the right boundary. So in particular, if you think about a local spin in the bulk, this will have exponentially small overlap with any of these two conserved quantities. And this also implies this exponential growth along the system, that this can only be an exact symmetry for open boundary conditions. Because if we wanted to solve this recurrence on top of being like periodic boundary conditions, we should also impose alpha j plus L equals alpha j for all j, but this is not possible for periodic boundary conditions, right? So we found that the system has some symmetry different from total charge or total, say, magnetization, which is exponentially localized. And the third option is the so-called quasi-periodic symmetries, and we will see what quasi means in this case. So in this, what happens is like you have two purely imaginary solutions of this characteristic equation, and therefore they are the conjugate of each other. So what this means is that instead of solving the recurrence, we can simply find, so we use these ansatz, and we simply solve for the set of roots of this function chi of k that will be really important in what comes next. And that's the reason I wanted to emphasize. So we just need to find this set of roots of this function. So what you will find here is that the solutions are periodically modulated along the chain with this kind of this cosine function in front, which, for example, let me give you some particular example to imagine how it works. Say I pick p equals q equals 1, such that we are in this third scenario, and say I fix the initial conditions to be 1, 1. So you will see for open boundary conditions, it is always a symmetry because I can always solve the recurrence to the right. However, for this particular case, it also happens that there's a finite periodicity on the lattice, as long as I cut the system in multiples of 6. So this will be also an exact symmetry whenever I use a system size that is a multiple of 6 for periodic boundary conditions. However, now you may wonder how general is this, because in principle, I could make any choice of P's and Q's, and well, it doesn't need to be the case. So if you want this to be a symmetry, you at least want to impose that this lies in the Brillouin zone, which means that at least this should be kind of a rational multiple of pi. And now you find two possible answers to this possibility. So the first of all is that this can only happen for particular cases of P over 2Q. So you can show this is the case, which means that this will be an exact symmetry for certain system sizes that fulfill this periodicity. Okay, so for example, for P over 2Q equals 0, this solution K star is pi half, and this will be only an exact symmetry for system sizes that are multiple of 4. Okay. However, for any other choice of P over Q or P over 2Q, any other choice that are most of the cases, K star is completely incommensurate for all finite system sizes. So what this means is that if you draw your Brillouin zone with the minimal resolution of 2 pi over L, this dot always lies in between two dots in the Brillouin zone. So, but when you take the thermodynamic limit, so L goes to infinity, this will become a better and better approximation, and eventually this will become an exact symmetry in the thermodynamic limit. Okay. So with this, we introduced the family of symmetries, and now our goal, following kind of this kind of inspiration from dipole conserving system, higher moments, etc., will be to understand the role that these symmetries have on the dynamics of the system, right? So, and the reason it's kind of meaningful to ask this question in the first hand is because it's our continuous symmetries. And we know they provide some long-lived modes to the dynamics. So let me tell you what this really means. So say we look at the spin-spin correlation, which is related to the local density of the conserved quantity. So in the presence of such conserved quantities, what you will find is that the correlation functions follow some scaling ansatz, given by some dynamical exponent set and some universal scaling function that depends on the ratio of spatial coordinates and time, okay? So for example, if you have particle number conservation and you don't have any other relevant symmetry, you usually expect diffusive transport of this local density. And this is described, and I'm writing this so basically what happens, like total charge is conserved. So if you create some initial modulation of the spin, this cannot be simply disappear. The system conserves the total spin, so this has to be spread out and transported across the system. So in this case, what happens is like the kind of correlation function that I'm writing here in momentum space follows this hydrodynamic equation, so this continuous equation. which basically tells that the evolution of this correlation is proportional to itself with some factor dk squared. So what this means is that every momentum that is not zero will exponentially decay. And for k equals 0, this is just a conserved, it is conserved, doesn't evolve because total particle number is conserved. And in general, from here, you will derive that indeed the real space correlation function follows this scaling ansatz with dynamical exponent in 1D 2 and a Gaussian kind of envelope function. However, if you have quasi-periodic symmetries, say you prepare this initial configuration with you tune with a wavelength that is exactly 2 pi over k star. Since this momentum is conserved, well, this shouldn't evolve at all. So what this basically this means, like, or what is the same is to say that although k0, like the total spin is not conserved, there are some finite modes that are conserved, which rules out, say, a naive expansion in the long, like in the, say, k limit of a small case, okay? So in order to kind of provide or solve what is the evolution of this correlation, we will assume a description in this in the spirit of hydrodynamics, and we will provide a kind of physically motivated ansatz, and we will say that the evolution of the correlation is again proportional to itself with some unknown function, such that the real space correlation or the long time limit is governed by the set of zeros of this function omega of k, okay? So if we take the limit of t goes to infinity, this will be governed by the places where omega of k vanishes. However, we still need to say what this omega of k is, right? So let's put some requirements. So first of all, we know, we first of all know that this function chi of k that appeared before, this tells us what are the conserved modes. So we want that whenever that function vanishes, this omega of k also vanishes. Secondly, we want this omega of k to be non-negative because we want to have physical meaningful solutions. Finally, we would like to predict the long time behavior, and this is mostly like a kind of mathematical requirement. We would like to be able to do expansions around the set of zeros. And finally, hydrodynamics is really about predicting the long wavelength, long time behavior of a system, and not so much about higher order correction. So we would like to be able to capture the leading terms. So it turns out that the choice of omega of k to be proportional to the modulus of chi squared is a meaningful choice, which, I mean, you can check for kind of previous works for U1 subsystem symmetries or dipole moment. Sure.
Can you remind us what chi was?
Yes, sir, that is a good question. So the set of roots of chi signal the conserved modes. Okay, so it appeared when we were here. It appeared when we were solving the recurrence equation in the case of quasi-periodic symmetries. And then we said that if we use this ansatz, it will be exactly the same as solving for the roots of chi of k. So this chi of k is really signaling and indicating where the conserved modes are. And that's the reason, since these are conserved modes, we would like this omega of k to exactly vanish at those points. Okay, is that?
Yeah, thanks.
Okay, thanks. So let me, let's apply this approach to the set of quasi-periodic symmetries that we found, okay? So here we know there are two conserved modes. So this omega of k will be just dk squared, where delta k is just the distance to any of these conserved quantities. And from
can
here,
I ask a question before you continue, so I don't
please.
stop you later? Can you please show the previous slide? So, because you're going a bit too fast for me, but to understand correctly, what you want to do here is try to find the continuous way to derive the scaling behavior. Is that correct?
Yes.
I see, and you're suggesting that if you try omega is equal to
yes,
chi, the roots to be the same. Okay, good, thank you. Yeah.
Yes. It's actually, I mean, it's, so I don't want to go into much detail, but it's, so the thing, like, it's a bit tricky because, like, when you do kind of usual hydro, you can assume, say you have some discrete evolution and you can take the limit of kind of the lattice spacing to be small or some kind of long wavelength limit. But here is these finite modes at precisely this particular place, and you would like to be able to exactly capture those modes. And in order to do so, that's the reason we impose this condition on the omega of k to be signaled to coincide with the zeros of chi. So if we apply these ansatz to the quasi-periodic symmetries, what you find is that omega of k is this delta k squared. And what happens is that, well, you naively would say, well, this is just diffusive scaling. This 1 over square root of t decay of the autocorrelations and some Gaussian envelope function. So this is indeed what you find in the numerical results. And then we also saw that if you choose a Q and a P that are not commensurate with the system, well, these are not exact conserved quantities. So there will be at some point, some time that the system will realize that it's not exact. And for, say, sufficiently small system sizes, for the time scales we consider, we'll go from this power law decay to something faster, some exponential decay of the correlation. Okay. However, if you really want to have an overall picture of what is really going on, one should rather look at the spatial correlations at different times. And what you find there is that this correlation, apart from this scaling behavior, has some additional modulation at the kind of lattice-scale distance given by 1 over k star, which lies on top of this Gaussian envelope function. So here, what we are plotting is some scaling. So we are multiplying by square root of t the correlation, divided by square root of t the x-axis, and then in usual diffusion, you should expect to find some Gaussian, and all of these curves at different times collapsing on top of each other. However, if you have these short wavelength modulations, with some additional features that cannot be collapsed, and which, if you validate by doing, say, the Fourier transform at some particular time t, you will find that indeed all modes decay, except those that correspond to conserved quantities. So in fact, this is reminiscent of something they called the UV-IR mixing. So this would be some kind of hydrodynamic analog, which basically means that you provide a long wavelength description, some effective description of your system, which still depends on lattice-scale features or ultraviolet features of kind of this microscopic theory. So we saw what the result is for quasi-periodic symmetries, and let me now discuss for exponentially localized symmetries. So in this case, well, this chi function has no zero. So if you wish, this exponentially decays means that we have a momentum that is purely imaginary, right? So you can think in that way, or simply you can think that since these exponentially localized symmetries are exponentially localized at the boundary, they have a really exponentially small overlap with anything in the bulk, and therefore you expect some exponentially fast decay. However, by the same intuition, you would say, well, if there's some local spin, some spin at the beginning localized close to the boundary, it might not be able to spread towards the bulk, and perhaps you also find some finite correlations at the boundary. So indeed, what you can show, so you can numerically test that this is the case. So the boundary correlations indeed appear to saturate to a finite value for all system sizes. And in fact, you can use the so-called Mazur bound to lower bound the time average correlation at the boundary at infinite times for infinite system sizes. And again, in this case, what this is reminiscent of is the so-called strong zero modes that appear in the well, people working with the spin chase for topological quantum order, which basically would predict some exponentially decay correlations in the bulk, but some kind of boundary modes that would lead to the inertia of the spectrum in the presence of some additional anti-commuting symmetry. So although I'm here discussing this completely kind of a stochastic classical system, if you think about the quantum Hamiltonians, all these have this additional anti-commuting symmetry, and therefore this could be think at least as a really close relative. I mean, there are some subtleties of strong zero modes. So far I discussed this, well, the effects of the symmetries in 1D, and then you might think, well, is this really, does it really apply to higher dimensions, or it's really dependent on the fact that you're using a 1D system, or even would you obtain some richer physics if you go to higher dimensions? And this is what I would like to talk in the kind of the rest of the talk. So there are two.
Before you move on, can I ask a question?
Sure, please.
With the danger of revealing various negative. I mean, so if I look, for example, at the plot on the bottom left, where you're plotting the t to the 1/2 Can you slowly describe how you obtain this? So, because I think I did follow, but I'm not 100% sure. But how can you describe what is being plotted and how you obtained it?
Well, this is a particular.
I know that this is what you
plot.
were doing earlier, but can you do this for?
Sure. So what we are doing is we generate an initial state. We take the spin, say, in the central site. We evolve this particular initial state, and we measure the spin in every other side of the lattice at every time step. Okay, so we have initial spin. We measure the spin in every side at every time step, and we keep multiplying these two to contain the correlations. So this we will obtain one run. Okay, so we will have a matrix.
So the zero in the first argument refers to what? K or X?
Okay, yes, this is the distance. So let me come back to the here. The serum is the central site, and R is any other side of the lattice.
Okay, so what you're plotting then in that figure is t to the 1/2 times c that you obtained literally by averaging over many runs.
Exactly, yes.
Okay.
By averaging over many runs. Yes.
Okay, and can you show the slide again? Sorry.
Sure, please.
Right. Okay, and then this is, so the plot on the bottom left is literally what you get by numerics, and you're saying that this, okay, so you're saying that if you were to plot the line predicted by setting omega k is equal to chi k for this particular set of p's and q's, you will get a line overlapping this. Is that correct?
Well, you cannot really obtain this number from the analytics. So from the analytics, you can obtain a scaling behavior, but you cannot obtain how fast. You can
I
feed
appreciate
it with
that.
this answer.
What I'm asking is what you're saying is that the qualitative behavior, the gradient basically here is correct. That is the point of this.
Yeah. That the
Okay.
kind of the prediction you can obtain from here. So this exponential case is even a bit stronger, but I will only say that the result is consistent with this prediction, because I think saying that we can feed exponential with the square root of t is saying too much. But from the analytics, what you obtain is that on top of this exponential decay, this omega of k has a minimum of k equals 0. So the total spin is not conserved, but still there's a minimum of this dispersion, which gives you this additional square root of t in the exponential decay. And that's the reason why we multiply the c by square root of t to show that this is consistent with a straight line. Okay, but this particular plot is more tricky than only the numerics. But yes. Is it?
Yeah, that's clear. Thank you. Yeah. I was
okay.
simply asking because you are going way too fast for me. That's all. Right.
Sorry. Oh, okay.
I just wanted to slow you down and give you time to think. Thank
okay.
you.
No, that is perfect. Thank you.
Question. On these same plots, on this same and the analogy with strong zero modes. So what you're showing is the inset is the correlation function of the span at the boundary.
Yes.
And it doesn't decay fully to 0, so its time integral will be non-zero.
Yes.
Okay. What happens if you go to the second spin? And I asked for the following. Oh, okay.
Sorry, please go ahead.
I asked for the following reason, because if you think of strong zero modes in the cases where you can write them exactly, like this transverse field Ising model, and the first spin has a very long exponential in the system size, defacing time, but the second spin doesn't, and the reason is that is how it's, how the strong zero mode object is as a CDS in terms of spin operators. So I'm wondering what happens here to the second or to the third, to spins which are not the boundary spin but close to the boundary.
I would expect the same to happen, to be finite but a smaller value.
Okay. So which I think it makes sense, because this is a much simpler density operator that's exponentially localized.
So in this case, we have like the analytics are really easy for the Maslow bound. And I think nothing would change if I do instead of boundary a bit far from the boundary, but it's still not the scaling with system size. So as long as it's not a fraction of the system size, but it's still finite number, the Maslow bound would still give some finite value. I think so. I think this is true.
Thanks.
Right. So we saw how it happens in 1D, and I would like to tell you basically the behavior in the higher dimension. So here, I will mostly focus on this first case, so quasi-periodic symmetries, where the upshot would be that you only not have one conserved mode, but infinitely many of them, which will relate with the physics of subsystem symmetries. And the second that is not published and is kind of ongoing work, but is, if there's time, I will tell you about, is the possibility of having structural modes also in 2D, where you can kind of do a similar analytics. And instead of telling about kind of generic, let me consider a particular example, okay, a particular model. So we will consider this two-dimensional system with gates acting on 8 spins, such that 4 spins at the outer square are moved to the inner square. Okay, so I'm using this color coding where blue means raising +1 and red means lowering by 1. So if you look at this gate or the evolution generated by these gates, you will find it has a lot of U1 conserved quantities. So first of all, the number of red and blue dots is the same. So this means total charge is conserved. If you look along the diagonal, this leads to these symmetric rearrangements of the spin, which leads to dipole conservation in any direction. And you can also show this system has conserved some quadratic moments, but not all, okay? Also, if you look along the particular row and column of the system, you will find that there are some subsystem symmetries. So it's not that the total magnetization along this row or column is conserved, but rather the difference in charge between even and odd sides. Okay, what is conserved? And that's the reason you have this additional -1 to the x modulation. However, what we want to answer is that are these all? So these are certain cases of modulated symmetries, but can we find, are there exists more? And we know that answering that question is the same, right? So we're looking for such conserved quantities, and we know that answering that question is the same as solving the associated recurrence relation. However, in 1D, we got some analytical insight, and you can solve in terms of the roots of the characteristic equation, but in 2D, to solve it generally, well, it's not so insightful, say, to solve a system of L-square linear equation. Instead, what you can do is you can use the insight that we got from the 1D systems, and we can consider 2 different answers. So we could have a modulation that is of the form e to the I k times r. So this would correspond to quasi-periodic symmetries. Or instead, we consider a modulation that is exponential in the 2 coordinates. So for this particular model, we can already rule out the second one. So believe me, this is the case. And instead, use really these ansatz to solve the recurrence equation. And again, this will be exactly equivalent to find the set of zeros of this function chi of k. So let me show you the set of zeros that this function has. So first of all, we have this central dot at kx, ky equals 0, which simply corresponds to the total charge conservation. We also have these boundary modes, there's infinitely many boundary modes at the boundary of the region soon. So at k equals x, kx equals pi, ky equals pi contributions, which by inverse Fourier transform, we can relate to the conservation of subsystem symmetry. So this makes sense. So if you think what is the most localized thing you can have in 1D, you just do like the inverse Fourier transform by weighting everything in the same way, and this will lead this to the subsystem symmetry. However, what is more interesting is that you have this additional set of quasi-periodic symmetries that form a closed loop in the extended Fourier soon, which again, most of the momenta are simply not commensurate for any finite system size, okay? But they are still there for open boundary conditions. And a bit kind of, well, so, okay, so this is the general ansatz. And now, as before, we would like to try to describe what is the long-time dynamics of the system given by these infinitely many contributions. So we will follow the same approach, and we will expand omega of k, which I remind you was chi of k modulus square, around the set of zeros. So what you find is basically 2 different contributions, okay? So you find first contributions coming from singular points. So those meaning places where 2 lines cross, or perhaps isolated points. So in places where two multiple lines cross, what you will find is that the autocorrelation decays in this fashion, so log t divided square root of t, which in fact was already found in some previous work with this U1 subsystem symmetries that I told you in the introduction, and which, well, appears to agree quite well with kind of the numerical results. And where everywhere else that is far from these crossing points, it basically goes as 1 over square root of t. And the reason why this happens, if you kind of want to understand how it works, in this case is that, well, this point, the contribution is 1 over square root of t because you have charge and dipole conservation, which in 2D leads to this 1 over square root of t. And far from these crossing points, you can think that doing an expansion along this line in the transverse direction is pretty similar to have a 1D system and doing an expansion around a particular mode. And then in 1D, we already saw we would obtain this diffusive behavior. However, as before, if we really want to understand the structure, we need to look at the spatial correlations at some particular time. And here what you find is instead of the rotationally invariant result that you would expect for dipole conserving systems, you find this weight that is highly localized along the primary axis. Okay, so this is the correlation between a point in the bulk and any other point, with these oscillations that do not appear to decay at infinite times. So from already, you can guess, like from what we got in 1D, this should correspond. So if we do a Fourier transform of this plot, this should just lie on top of this set of zero modes or the conserved quantity of this sky function, and is indeed the case. Okay, so well, what this was a really particular model, a particular example, but indeed this can be generalized to higher dimensions. For 3D, you would not have only 1D lines, but like surfaces, and the contributions to kind of the hydrodynamics will come from mostly from these crossing points, and this would give a rather rich behavior. And you can also have systems that, again, in 2D has no charge conservation at all, but only this set of finite modes. So you can have, say, closed loops or crossing of closed loops. So there's a lot of like really rich out of equilibrium, mostly dynamics.
Can I ask
Sure.
something? So,
Please.
so these orange lines are the zeros of this chi-k function,
Yes.
right? Mm-hmm.
Yes. Oh, actually, yeah, that is a yes. That are zeros of these chi of k functions. So what I'm plotting here, what I want to mean with this is like I focus on a particular model, but so let's say this way: you want to understand the dynamics of a dipole conserving system or of some system with these symmetries, and what I'm saying is that just knowing a bunch of features about how these lines cross and the structure, you can predict the long-time behavior of autocorrelations. So I'm not sure if I have time to discuss the 2D exponential symmetries, or I should rather go to the summary. It's in principle 2 slides. Well, it's a slide divided in 3 parts. So,
I mean, I think you can have 10 minutes more if you want.
Yeah, I think I will be faster, but I mean, yeah. So as I told you, so we found this strong zero modes in 1D, and the question is it really specific because we were considering 1D, or can we do the similar construction in 2 dimensions and have similar results? And in order to have some more kind of treatable model to be able to do some analytics and check with the numerical results, let me consider instead this model. So you can think it's the same as the previous one, but just squeezing the central 4 spins to just one side. So this is moving, say, 4 spins from the boundaries to the center. Okay. So in this case, you write the recurrence equation and you put it in a kind of a more suggestive way. You will find that after you fix some boundary conditions in this 2D square lattice, solving the recurrence is exactly the same as solving the discretized Laplace equation. So, and this has some exact solutions. And in particular, you can say that you can fix your boundary conditions for alpha to be 1 at some particular point of the boundary and 0 everywhere else. And you can do this for every point along the boundary. Another question will be, what happens if you look at correlations at some boundary point? Is it again the same as in 1D, or do they decay? And again, what we did is you can look at the mass rule bound in this case, which we can almost semi-analytically show to be, well, it appears to go to a finite value. And if you contrast with numerical results, what you will find is, again, while boundary correlations look to, well, bulk correlations appear to decay, following our kind of hydro approach, boundary correlations would get stuck at some finite value. And if you look at the spatial profile of these boundary correlations between the central point and everywhere else at the boundary, you would find that apparently is exponential localized in that particular point. So with this, I would like to finish summarizing what we did. So we introduced a new family of modulated symmetries of two different kinds. The first one was exponentially localized symmetries. Those led to something really reminiscent of these strong zero modes. The second family is quasi-periodic symmetries. It lead to really rich sub-diffusive behavior with these short wavelength oscillations that is kind of an analog of the URV-IR mixing that people, for example, currently are studying a lot for fractons and similar models. We provided some microscopic models to understand this behavior and some general description of the long-time dynamics. And as an outlook, that some parts we already started, but they are not really there, it will be interesting to understand the fragmentation or in this other reducibility of these 1D systems for exponential and quasi-periodic symmetries, and perhaps try to show whether they also lead to this localization in 2D. And it would be also really interesting to understand what is the role of these symmetries, say in the corresponding quantum models. So what is the role of the symmetry at low energy with all these infinitely many zero modes? And eventually, and this is the way I started the talk, I told you that these were rather unconventional symmetries and that you don't really expect to find them in anywhere. However, dipole conservation appears to emerge in certain strong tilt regime of interacting systems. So an interesting question is whether you could find a similar behavior for such modulated symmetries, whether there would be some regime, say on current experimental setups, that could in principle lead to this kind of effective behavior. And with this, I would like to really thank you for your attention. I will be really happy to answer questions.